Yesterday we started with basic concepts of filters and what are the various types of filters we have. And then so today we'll see a design example. So now you are able to see this. So yesterday we discussed what is RF frequency rate. So it is from 300 megahertz itself, and beyond 1 or 2 GHz, we name it as the microwave frequency band. And now we go up to the millimeter wave cycle. Till 100, 200 GHz, people are doing research and some commercial products are coming for defense application. So what are the design steps in a microstrip low pass filter? So, as I outlined yesterday, the first step is to design a lumped element filter. So, you have to use the same procedure what we have studied for a lumped element filter, low pass or high pass or whatever it is. And then you find out the values of the discrete component, the inductor capacitance value, and choose a prototype. You want. You may use a pi network, a T network. So you choose the appropriate prototype of the filter you want, and then apply the equations that is already been framed either under the image parameter method or insertion loss method, and arrive at the values of the inductor and capacitor, and just make a lumped element circuit, and you can verify the frequency response whether it meets your spec or not. And then we can do a transformation from lump component to distributed component. So each inductor capacitor can be transformed into a equivalent microstrip line map. So that's the thing. Even though you are going to design a microstrip filter, first you should design a lump element filter. Okay? And arrive at the values of inductors and capacitors, and you choose the prototype one. Prototype means what type of network you are going to use. A pi network, a T network. There are different prototypes of filters available. So you should use the equations for the particular prototype and arrive at the values of LNC. And then we're just going to transform that inductance and capacitance, or realize that inductance and capacitance using microstrip lines. So that's the step. So here you could see a popular low pass filter prototype. This is a ladder network, called as a ladder network, and this is a topology for a low pass filter. So two methods are possible, where you can have the inductor followed by two conductors. This one for configuration, or else two inductors with a shunt capacitance. So that's another configuration. So you can choose any of this. There's no difference in the components. So for our example today, we are choosing this two shunt capacitor and one series inductor. This topology we are taking up for our example. So this is the first step. You fix which topology you are going to use to design your low pass filter. Right. Then, which type of response you need for your filter? That's a second thing to be considered. So we know there are 4 categories of filter response. Be it high pass, low pass, whatever it is, based on the response of the filter, not the frequency response, based not on the cutoff frequency, actually, based on the ripples in the pass band and stop band. We have 4 types of filter response: Chebyshev response, Butterworth response, elliptical filter response, and one more thing is also Gaussian filter response. Okay. So there are 4 popular filter response. So in this, mostly Chebyshev and Butterworth are widely used. And what's the difference between them? It's the same network actually, but the way you choose the values of the components, you get different response. And it is obvious from the graph that if you design a Chebyshev pass filter, you could find some variation in the pass band. Do not get confused with the response here. The response looks like a high pass filter when you look initially, but the y-axis is attenuation and not the gain actually. So if the y-axis is gain, then it could be a high pass filter. But here the graph is shown to be attenuation and the frequency. Right? So a low pass filter will have lower attenuation in the pass band. That is at the low frequencies, and then higher attenuation beyond the cutoff, right? So it's a low pass filter. Similarly, for the Butterworth filter, also at low frequency, the attenuation is lowest, and then it increases beyond the cutoff frequency. Omega C is the normalized cutoff frequency. So you could see the difference here. In the Chebyshev response, you could find some variation in the attenuation. And even this reflects in the gain also. So the gain of the filter or the attenuation filter is not constant. It just varies. Slightly there is a fluctuation. We say it is ripples actually. But the transition from cutoff frequency to that stop band is more quick actually. It's at a less frequency, less window we could say. It could reach or switch over to the stop band. So the transition is faster. That's what we observe here. But the drawback is you have a variation in the gain of the filter during this pass band. But if you come to this Butterworth response, the response is flat. Actually, there's no ripples here. The gain is constant or the attenuation is constant throughout that pass band. And then beyond cutoff, the attenuation gradually increases. But the rate of increase of the attenuation is more gradual in a Butterworth filter. So it doesn't suddenly steeply goes up. So it gradually goes. So the implication of this is that, so even beyond cutoff frequency, there is possible that some high frequency components will appear at the output with some degree of attenuation. But you get small values of the high frequency component that appear at the output. This is its drawback. So you should, to increase this transition rate, we should have a higher order filter so that the transition slope can be increased. So based on application only, we can decide whether we have to use Chebyshev or Butterworth filter. If it is an audio kind of thing, a Butterworth filter is more recommended because the gain should not vary when you are listening to some music or something. So when you select some volume, but the output will change with different frequency, will have different sound when you use a Chebyshev filter. So for audio applications, people do not prefer using Chebyshev. But coming to the wireless applications where we have to filter a specific frequency and allow only that required bandwidth of the signal, then Chebyshev would be preferable because it would effectively cut off all the signals beyond its pass band. But Butterworth will allow, right? Butterworth will allow some signals beyond the cutoff frequency with some degree of attenuation. But Chebyshev will strictly allow only the signals within the band because the transition is too far. And you can ask, what about the variation? But in a wireless system, this can be made constant with the equalizer. You may have amplified using some equalizer kind of thing, we can make it constant. Right. So you have to choose. You have chosen the prototype, which prototype you want to use to design your filter. Then response, which type of response you need. And based on the response, you have to select the design equations. So, in the reference book, which I have put at the end, you can find the design equations for the transfer function, ripple factor, all this you can find. So to start with, if I'm going to design a filter for Chebyshev response, so this is an equation for the transfer function. This is a transfer function for a Chebyshev response. And this is the ripple factor. LAR means ripples in the attenuation band. That's in the pass band. What is the ripples? So how much ripples you can allow? So you have to assume that what is the allowable value of the ripples. According to that, you can find out the LAR value, or from LAR you can fix the X. Mostly you fix LAR and then you find X. But Then from this transfer function, you should arrive at the equations. We have to find out the filter coefficients for the Chebyshev filter using the equation given in this. So the number of the coefficients will increase with respect to the order of the filter. So if you are going to use more stages of your ladder network, then obviously you have more elements, and this G0, G1 are actually. So G0 equal to 1 corresponds to the source impedance, characteristic input, P1 generally. It's a normalized one, so it is 1 actually. Then G1, G2 are the coefficients with respect to the other elements in the network. So G1, G2 refers to each element of the ladder network. For example, in this case, this G0, which is the source impedance, and G1 is the first element, G2 the second element, G3 is the third element, and it goes up to n plus 1. So this is a generalized equation to find out the value of G for each element, for given order of filter, because you have to fix how many elements there will be in your filter. So order is decided by the number of elements we use in the ladder network. More the order of the filter, what is the advantage? And if I may ask what's the advantage if I use 2-stage, 3-stage, 4-stage, like that. As you increase the order, this transition band, that gap will be less actually. So the role of rate will increase. The transition from the pass band to stop band will be too fast if you have a higher order filter. Okay. So it is desirable to have a higher order filter actually. You may have n equal to 10, 20 like that. It is because if you choose that, you can allow frequencies within the pass band. Stop band signal will not come, only the pass band signal will go to the output. But what is the drawback when I choose a higher order of the filter, say n equal to 20 something if I choose. When you choose n equal to 20, then you have more elements in the ladder network, 20 elements in the network. So the signal has to pass through the 20 elements and it will be lost in each element. Right? So at the output, the signal level will be too less. So the overall reduction in signal strength will be very less because a passive filter could not provide you amplification. So whatever you give from that, the signals will be lost actually. So if they are implementing with discrete component or even a distributed filter, people will not go for higher order, maximum 10 or 11. That 11 is also too high actually. So maximum 5, 7, that's the order they used to fix. Beyond that, they will not go because your signal will be lost actually. But if you take the DSP filters, you might have some knowledge on the DSP filters, right? There, it's a software kind of thing. So with DSP filters, you can have a higher value of n actually. You can very easily design a filter for n equal to 100, n equal to 50. But the signal loss will not take place because it's just a delay element you are doing. It's a cumulative addition multiplication we use in a DSP filter. So losses will be very less in a digital filter. So a digital filter performance will be superior to this analog. Whether you implement in microstrip or discrete components, analog filter. Here we cannot have higher order actually. But in a digital filter, that is with the DSP if you implement, you can have very easily n equal to 50, 70, even 100 you can have. So you could see the transition will be very sharp and it will allow only the signals that are in the pass band, and beyond the cutoff frequency, only less component will come into it. So filtering will be more perfect in the digital domain. That's why people nowadays use SDRs. SDRs, we convert our received RF signals into digital, and then we implement most of the communication tasks in the software itself. For example, IF amplification, down conversion, all this now people trying to use in the software domain because the digital systems can perform very well than So digital filter design is not difficult. Okay. So first step is choosing the network, then there is a response. From the response, you identify or you have to calculate the coefficients G0, G1. For a given order, you should do this actually. And there is a guideline for choosing this order. So the order of the filter is decided by your ripple factor in the pass band and the attenuation passband and the stop band. So how much ripple you want, based on that, the order of the filter will change. So this is the equation that used to find out the order of the filter. So nowadays, many toolboxes are there using which you can get all of this. And one more thing, people have created a table. So using these equations, even the book itself, you can find a design table. So they themselves have calculated the values of G0, G1, G2 for the standard value. There are ripple in the attenuation band, which is 0.01 dB is permitted. This is more than enough for practical consideration. So G0 is always 1 actually, because it is the source frequency that is always 1. And then you plot the values of G1, G2, G3, and so on for various n you plot. See, if n equal to 2, then you have 3 elements here. So along with this G0, you have 4 elements. So n equal to 3, you have 4. So based on the order, the number of coefficients will change, and the length of the filter will be larger. So why they have stopped at 10, as I said, in the analog filter, they will not go for higher order. So n equal to 10 itself is more than enough. And this is a case for Chebyshev filter. If you are designing a Chebyshev filter, you can find, if you choose n equal to 3, then you get G0, G1, G2, G3. The values you can readily take from the table instead of using this equations. It's more tedious to solve this equation. So straight away you can arrive at the filter coefficients from this standard table. And if you are interested in designing a Butterworth filter, then these are the design equations for that. For design equations in the sense for the filter coefficients actually. And then this is the equation for finding the order of the filter based on what is the stop band ripple you want. So the cutoff frequency and the stop band ripple what you want to get the start of the filter. And actually, I told in Chebyshev there will be ripples in the pass band as well as the attenuation band, but here you could see L, B, S, there is no R here because there aren't any ripple in the Butterworth filter, so it is simply the stop band attenuation. So how much attenuation you want in the stop band is more important because the Butterworth filter will allow some frequencies beyond the cutoff with some reduced attenuation, right? So you should choose a higher value of attenuation in the stop band for this Butterworth filter. So for required stop band frequency and the stop band attenuation level you require in the stop band, you can find out the order actually. Then once you know the order, you can find out the filter coefficients. And again, it is tabulated for attenuation ripple. It's not ripple. For attenuation of 3 dB, the stop band. They are given a table here. So here also they are given the filter order up to 9. They are given the coefficient values. So as I pointed out earlier, either you choose this Butterworth response or Chebyshev based on the application. For RF, where exact filtering is required up to the cutoff frequency, Chebyshev will be fine. Audio applications where the gain has to be constant, Butterworth will be to that. So in our case, we are going to design for a higher frequency, RF frequency. So most probably it would be a Chebyshev filter because in RF, it involves in the communication system, right? So people rarely use Butterworth filter in the RF domain. So I too have taken a small example in the macro region. So what's the specification we have considered for our filter design is cutoff frequency up to 1 GHz. It's a low pass filter. It has to allow up to 1 GHz. And pass band ripple is 0.1 dB. So generally, this is a Chebyshev filter, so ripples will be there. And we have taken the standard table, which is given for 0.1 dB. Our return losses minus 16 points. So it means the variation would be 1/10 of the peak value, 0.2 dB. The variation would be within 1/10 of the peak value. And source and load impedance, it is considered to be 50 ohms. So our filter has to get connected to a 50 ohm source. So based on this passband ripple, you can get the order of the filter. Then from the order of the filter, you can get the coefficient value. So from the table only, these values are obtained.
Network issue.
It's audible or not? Can you all hear me? Okay, I'll proceed. So the coefficients are obtained from the table. Okay, so you'll be having different tables for different passband ripples. So you have to get the filter table for this, and you can take out the coefficients. So this is our counter filter structure. So we need there are 4 coefficients in it: G0, G1, G2, and G3. G4. 5 elements. So that includes its source resistance as well. So this is going to be the circuit which we are going to design. We have G1, G2, G3, and so once you got this, what we have got is the coefficients, filter coefficients, but we have not yet arrived at the inductance and capacitance value. Okay? So once you have the coefficients, then there are we choose the prototype first. Based on the prototype, we choose the response, what type of response we want, and then from the response we arrive at the coefficients of the filter, and you can use this table available for a given attenuation band ripple. Actually, it would be more than enough for designing up to n equal to 10. Actually, in analog filter, we won't go beyond this. So, and this is a coefficient equation for Butterworth response. For this also, you have a table from which you have to find out the coefficients. So now for cutoff frequency of 1 GHz and passband ripple, we have to find out the order, and then for the order n, we have to get the coefficient value actually. So here we have n equal to 5 actually. So we have G0, G1, G2, 4 elements being used in this. So this is an example we have taken, and from the coefficients we have to find out the value of the inductance and capacitance for your network actually. Okay. So we have a shunt capacitor here, and this G3 as the shunt capacitor, and G2 and G4 are the inductance. The circuit we have here is not, this is the right answer. So we have inductor L1, the shunt capacitance, and then inductor L3. This is the exact topology, and the microstrip equivalent would be like this. We'll come to this later. So again, you have equations which can be used to find out the values of inductors from the coefficient value. Here you have L value and C value could be obtained from this generalized equation for Chebyshev filter. So we have here L1 equal to 8.2 nanohenry and C equal to 3.6 picofarad. So the problem here is we may not have a discrete component for this value. In simulation, we can do. We can pick up the component, assign the values, and simulate. You'll get the response. But in realization, we won't get discrete component for this low value of 8.2 nanohenry. It is not possible, and even it would not make with a coil also. In nanohenry, it's not possible. Microhenry also difficult actually for manually making them. So how we can realize this filter is the only goal is the microstrip line. Right. How to now the next step is how to transfer our lumped element circuit. We got the lumped element circuit and its values, and how it can be converted to distributed element. Right. So for this, the 2 steps are involved in this actually. First one is the Richards transformation. So what Richards transformation, what he proposes is that a lumped element can be represented as a short circuited or open circuit transmission line. That's what Richard's transformation says actually. So you can use a transmission line which is short circuited or open terminated to replace a discrete lump inductor and a capacitor. So that's the relation. Inductor is equal to a terminated a transmission line of certain length, and capacitor is equal to a open end transmission line. So the job is now to find out what is the length of this transmission line that has to be used to replace this inductance and capacitors. So a more simple approach of realizing this inductors and capacitors in microstrip is stepped impedance technique actually. So in stepped impedance, what we do is we use a thinner or a wider microstrip line to realize inductance and capacitors. It's very simple actually. So we can use a thin line to realize an inductor and somewhat a wider line of the microstrip to realize a capacitor. And this is what you see in this picture now. If you have a ladder network, you know what is the length from the lump circuit you are arriving at this. So this can be very simply replaced by a microstrip line with different widths. That's all. So now the job is to find out what is the length of this line, what is the width of this line L1, which will replace this inductor actually, and then what is the width and length of this broader microstrip line, which could replace this capacitor. Then what should be the length of this? We have the same value, right? So simply we have to duplicate. Once you find out L1, we have to simply duplicate the values. If you know these three values, this same structure will get duplicated for any length of the ladder network. So this is the job. So it's a very simple. There are other methods also. You have the stub technique where we can replace that inductors with stubs actually. The stub is nothing but a projection in the microstrip line. You have a constant width microstrip line running out, and then you have projection from that line that will implement the capacitors. But this one is a more simple technique. Okay. Right. So now how to find out the length and width of this transmission lines to realize inductor and capacitor. That's the job we have to discuss. So this microstrip implementation here uses cascaded structure of alternating high and low impedance transmission. So it's a common terminology in microstrip line to indicate this thin line is a high impedance line which will implement a inductor actually. So this broader line, it's the same line, just the thickness is here. This broader microstrip line is called a low impedance line, and it will replace it will act as shunt capacitors. This broader microstrip patch over here, what you see, the broader microstrip line will act as a shunt capacitor. That's all. So this is a high impedance line, and the broader one is generally called low because its impedance will be less. If the microstrip line is wider, its impedance will be lower actually. If it is thin, its impedance will be high actually. So it is a high impedance line. So we are simply using a high impedance and low impedance microstrip line to realize this lump element inductors and capacitors. Okay, so this is how we get the value of L1, L2 from the filter coefficient. And okay, so if you want to find out this length and width of this microstrip line for high impedance and low impedance, you should fix what material you are going to use. What is the substrate material you are going to use to implement this filter actually. That's very important. Okay. So it's an assumption actually. So it is a 10 point because it's a PCB structure. It's not FR4. It's a different PCB material whose dielectric constant is 10.8 and the thickness is 1.27. Generally for antennas, no, we have lower permittivity, but for transmission line, if the microstrip line is used as a transmission line structure, then they prefer having a higher dielectric constant, because higher the dielectric constant, the radiation from the line will be less. So leakage from the line will be less actually. So a filter should not radiate energy into the space, right? So it's preferable to have a higher value of dielectric constant. So you should choose, if you are implementing a standalone filter, then you should choose.
So kindly repeat the point, so please.
Okay. Generally, in microstrip, and if I say we use RT duroid or FR4 material. In RT duroid, the dielectric constant is 2.2. In FR4, it is 4.4 actually. For antenna design, the microstrip material, that substrate material what you use, should have lower dielectric constant for effective radiation. The radiation efficiency is better when the dielectric constant is lower actually. But if you want to suppress in a microstrip filter, is just a transmission line. It is in the path of a transmission line. So the energy should not escape. Whatever you give, it should go to the load. The other section could be amplifier or a mixer, that kind of thing. So as it travels down the filter, the energy should not leak out or should not get radiated into the space, right? So we should use a substrate material which will have a higher dielectric constant actually. So these are two difference. In filter, it's preferable to use materials that have higher dielectric constant. The performance will be good. The leakage will be less actually. So thickness is same. So say same PCB structure will have 1.6, 1.27, but whatever is available, you can use. If you have a material with higher dielectric constant, you can go for it to get better performance. Okay. Suppose we are insisted to do on FR4, which is 4.4, then no, there go. We have to implement with that. But if you are making a standalone, a separate module of filter with a box kind of thing, you are making a standalone filter, then you can use such materials actually with higher dielectric constant. The gain will be superior and the losses will be very less if you do that. Okay. So we need a high impedance line as well as a low impedance line, right? So it's high impedance means it should be higher than this Z0, and low impedance means it should be lower than this Z0. And we know Z0 is 50 ohms. That's the source impedance. It is 50 ohms, right? So here this line should have a characteristic impedance higher than this Z0, 50 ohms. And for C2, the line should have characteristic impedance lower than that. Okay? Because if you want to find out the length and width of microstrip line, first you should know the impedance. If you know the impedance, you can easily get the values of length and width of that line by using a microstrip line calculator. Okay. So based on this consideration, for this also there is a toolbox. If I want, if I give what is the thickness of substrate and then what's the dielectric constant. So here the high impedance is chosen to be 93 ohms and the low impedance is chosen to be 24 ohms actually. So this is the impedance required for this inductor and the capacitor. So it should be higher than your Z0, 50 ohms. For capacitance, it should be lower actually. Okay, so we have chosen 93 ohms for that inductor high impedance line and 24 ohms for the low impedance line actually. So from this value, you can find out the length and width. So now you can calculate what is the length and width of the microstrip patch to realize an impedance of 93 ohms. Similarly, you can find out the width and length to realize 24 ohms impedance. That will be your capacitor. Okay. So this is going to be the impedance of the capacitor, shunt capacitance, and this is going to be the series inductor. So this is a general approximation. So when I say high impedance line and low impedance lines are used to realize L and C, I refer with respect to the characteristic impedance Z0. So one is chosen to be less than that, the other one is higher than that. And it should not be too high, so it should not be double that. So it should be less than double the 50 ohms. So 50 means it should be less than 100 actually, you should go beyond that. And 25 ohms, 20 ohms is the limit we can have in the lower bound. There are relations to find this actually. I didn't put that, I will share you. Okay. So now we know what is the value of Z0L, actually the low impedance value. We got what is the value of the low impedance line, and we know what is the frequency value that has to be realized, L value, and this is the guide wavelength. Because you know the frequency, you can calculate the guide wavelength, because the guide wavelength is the wavelength in that my substrate material, because we have chosen substrate material with epsilon r equal to something 10.8 here. So you have to find out the guide wavelength for this particular substrate material, and this will give the length of the transmission line for higher. This is at OL for inductance, higher impedance. And similarly, you will get the length for the lower impedance, Z0 C for the capacitance. Okay. So the other additional factors required is what is the value of C you are going to realize, what is the cutoff frequency, it is 1 GHz taken, and this is C value, this is L value, lambda G is the guide wavelength. So you know the frequency, cutoff frequency you take, and then you find out lambda G by substituting that epsilon R. You have relation between guide wavelength and free space wavelength. So this is the relation. You'll get this lambda G, and you'll get the length of this line for implementing capacitor. So for our example, it turns out to be 11.04. This is the length for the inductor, and LC is the length for realizing the capacitor. Then the next job is to realize the width actually. Okay. And lower equation is more accurate form of this actually, but this could be enough. What we have seen in 5.1 and 5.2 is more than enough. For more accurate realization, the below equation can be used. So now you got L and C, right? So once you get the value of L and the impedance, you can find out the width also. So this table shows what is the low impedance value. It is 24 for that. Source impedance is 50 ohms and higher in the 93. This guide wavelength for that is with the capacitance of the guide wavelength. Lambda GL is this. Lambda G0 means free space for the source impedance, and lambda GC is 105. And for this parameter, WC is 4 here, and W0 is 1.1, and for this 50 ohm it is 1.1, and for WL it is going to be 0.2. For inductance it is 0.2. For source impedance of 50 it is 1.1, and for the capacitive impedance of 24 shunt capacitance it should be 4. And length we already have it. The length for inductor is 11.04, and length for capacitor is 9.75. So you could see the filter. So this is the line for 50 ohms. This is a line for 50 ohms, and this is a line for the inductor value. You know the length is 9.81 and width is 0.2, and this will give overall impedance of 93. This is designed for an impedance of 93 ohms, and the second one, which will replace the shunt capacitance, will have 7.11 as the length and 4 mm as the width. This will realize the shunt capacitance. Again, this is a repeat of the same inductor here, and then we have the 50 ohms load impedance. So this first one is the source impedance. Next one, the last one is the load impedance 50 ohms, and this is the inductor equivalent. This is a capacitor equivalent, and again inductor L3 actually. And if you simulate this in by creating the structure in the microstrip, we'll say HFSS, and we can expect this response. So this part I will show tomorrow actually. Today I didn't get time to do the simulation. I will do it and show it tomorrow. And similarly, you can go for high pass filter actually. So for high pass filter, there is different topology. Actually, the topology will be different for a high pass filter, and we can do simple. The values can be transformed actually. We can transform the values to high pass filter. That we'll discuss tomorrow regarding how to transform this circuit into a high pass filter. We'll discuss. Yes.
Sir, excuse me.
Yes, sir.
How
yes,
can
sir.
Sir, one dot have.
Yes.
How we are calculating the width of the transmission lines, sir, here?
Okay. So width of the line we can get from, okay, you got the impedance, right?
Yes,
You
sir.
know the impedance, right? impedance
Yes.
of this and impedance of capacitor. So
Yes, sir.
you can have a microstrip line calculator. For W, I have not put the equation because it is obtained from that online microstrip line calculator. So if you give the impedance, it will ask for the impedance. If you give the impedance, frequency, then that substrate dielectric constant,
Yes, sir.
you get the value of length as well as slit factor. You get it.
Okay, sir. Okay, sir. Thank you.
A
Thank
formula
you.
is also there. I forgot to include. I'll
Okay, sir.
share this PPT also to all the
Okay, sir.
participants. Okay. If possible, tonight itself, I'll make this video of the simulation and share with you, so that tomorrow we can discuss high pass and band pass examples. Okay. Any other question you have?
No, sir. Thank you.
Okay.
So will you
Thank
do
you.
simulation
Yes.
on this?
Yeah, the simulation today I couldn't make it because of other sudden commitment. So
Okay, sir.
that's what I will make it and share the video. And tomorrow I'll do live performance for high pass filter. So similarly, we take a high pass or band pass filter. I'll take band pass because high pass design is similar to this. I'll just give an overview how you can convert this to high pass. Then I'll demonstrate a band pass filter in ANSYS HFSS.
Okay, sir.
And for this, I'll share the video. I'll make a video and share it.
Okay, sir.
Okay, sir. Thank you.
Okay. Thank you all.